Hello, my name is Murad Al-Arabi. In this tutorial, I will show you how to program Newton-Raphson and the finite differences methods together in order to obtain the roots of higher degree equations. The tutorial layout is as following. So we'll see the simple iterations method as algorithm code. Then we'll discuss Newton-Raphson method, finite differences method as formulas and codes, and finally we get the script and function of the solution of the higher degree equations by combining the codes of Newton-Raphson and finite differences methods. Let's start with the simple iterations method. The algorithm of the simple iterations method starts with the rearrangement of the equation so that the variable is put on the left side. For example, we have here the quadratic equation x squared minus 2x plus 8 equals to 0. So in order to formulate it for the simple iteration method, it could be put in two forms. The first form is x equals to 0.5 x squared plus 4 by taking the linear term to the left side, or by taking the square term to the left side, we can get the form x equals to square root 2x minus 8. Now, the second step is to assume an initial value to start the first iteration. The initial value is generally selected according to the expected or predicted value of the root. So there's not a certain rule to select the initial value. It depends on the prediction. 3. Substitute the initial value in the right side of the equation and calculate a new value for the variable. 4. If the absolute difference between the new and old values of the variable is larger than the given degree of accuracy, so we should at the beginning assume a degree of accuracy or tolerance, and we compare the absolute difference between the two values of x, for example, with this tolerance. So if the difference is large, so then we should consider the new value in the next iteration. Repeat steps 3 and 4 until the solution is obtained. Let's illustrate this algorithm up to this point in this simple illustration. For example, if we have this form, x in u equals to 0.5 x squared plus 4. So first we substitute the initial guess right side. This will yield a new value for x. We compare these two values to each other to see if they're approaching to each other. If they are not close enough according to the degree of accuracy we assumed, then we should take another trial. In the next trial, the value of x in u will go to the right side, and so on. This loop or this cycle will continue until we get the solution, or if the new value does not approach the old value, in other words, the difference increases in each iteration, at the end of the maximum number of trials, stop. So that means the solution cannot be obtained by this initial guess or by this form. So try another initial value or another rearrangement of the given equation. Now, let's see this algorithm and how to be coded in MATLAB Octave by solving this problem. Find the roots of the following equation: 2x squared minus 5x plus 3 equals to 0. We have two roots, x equal 1 and x equal 1.5. These two roots are obtained analytically, and mainly we do this because we need to verify our solution to know if the numerical solution is correct or not. Then we apply it to the other problems. So here, first step, we make two forms from this equation. The first form from the linear term and the second form of the square term. When we get these two, and let's start with the first one. So let's go to the IDE of the of Octave. Here we see the editor on the left side, and we see the command window at the lower right side, and we'll try to code this problem and by using to solve it by using simple iterations method. So first, let's define the function. So we say function f, call it simply f, equals to, this is an anonymous function. That means it's a single one-line function embedded in the MATLAB Octave code. So here we say 2x squared plus 3 over 5. Okay, now let's define the initial guess. To simplify the explanation, I will go to the previous page here in order to take the steps of the algorithm one by one and apply them in our code. So the second step will be definition of the initial guess. Let's say it's 0. Now let's define the value of degree of accuracy, the tolerance. The tolerance, let's say tol, equals to, should be a very small number. Let's say, for example, 1. Maybe too small, maybe. This depends upon the kind, or let's say the type of problem you're solving. Sometimes accuracy up to maybe 2 or 3 decimal digits could be enough, and sometimes we need more. So this is up to the problem to be solved numerically. We have loop here, so we need to make a loop. Now we should select, we have two types of loops in the computer programming in general. We have the for loop and we have while loop. Since in this problem we have maximum number of trials, so we need a counter and we need a limit for the number of trials. So for loop is the best choice in this case. So we say iteration equals from 1, let's say 100. Now we go to the third step in the algorithm and we say that x u equals to f of x. So here we substitute the value, given value x, in the right side. Now we come to the condition. So condition says the absolute difference between x and u and x, if it is larger than the tolerance. This is the translation of the let's say algorithm. So if absolute difference between x and u is larger than tolerance, then let x equal x nu. Here we don't need equality. Here we mean that we take the value of x nu and assign it to x in order to use it in the next iteration at the right side. This is the meaning, or let's say this is the mechanism of this algorithm. So we say else, if this condition is not satisfied, that means that if the difference is equal to the tolerance or less than the tolerance, okay, that means we have obtained the solution. So we don't need to go in the loop anymore. We can stop here. So we say break. Break actually will end the loop. So end. So here we have two end statements. The first end to end the conditional if, and the second end here in order to stop or end the loop. Now let's display the both values. We can say f printf. This is a function for output the results or anything in the MATLAB octave. So f printf, and let's say x u equals to, well, let's say the root equals to f at iteration number n. So this is sentence which will be displayed in the command window. So we define the x nu and iteration. So this is, let's say, the direct translation, the direct transformation of the algorithm into MATLAB octave code. Now let's run the code and see the output. Okay, so root 1 is obtained at iteration number 60. So this is the solution by using the simple iterations method. I used, this is the file name. I called it Newton-Raphson because we are discussing Newton-Raphson method in this tutorial. But this method now is called the simple iterations method. In order to get the second root, because we know that this problem has two solutions, 1 and 1.5, so let's try at the beginning to substitute, or let's use another root or initial guess, sorry. So let's, instead of 0, let's say 1.2. And we run the code. So 1.2 gave us the same root 1. Let's use 1.4 again, although it's closer to the second solution. Let's use 0.8, infinity. So we see here that the value is infinity. So actually, this form, the first form of the equation will not give us the required root. So let's change the form here and use this square root, the second form, see if it will give us the solution, not x, minus 3 over 2. Now let's run the code. We don't have to change first. That's 1.8 as a first guess or initial guess. Very good. So it gave us the solution 1.5 at 71 trials. Let's try, for example, 0. See? Actually also 1.5 at iteration number 80. So here that means that we need to change the form in order to get the second root. So simply this is the simple iterations method. It's directly applies the change in the equation, and then we have to make some trials until we get the solutions. Sometimes the given initial guess or the given form or the found form does not give the solution, and then we shall try another form. Now let's discuss the Newton-Raphson method and see how to apply this method to our code. So the Newton-Raphson method has the same procedure of the simple iteration with the main difference in the step number 1. What's the difference? The difference is instead of simple rearrangement of the given equation, a new equation should be formulated by using the given equation and its first derivative. So here we need to make differentiation in order to get the formula of Newton-Raphson's method. So this is the formula of Newton-Raphson. This is the, let's say, the simple algorithm somehow. So here x and u will not equal to different, or let's say a formulation by taking to the left side or so on. No, here we are saying that x, old value equals f of x, the given function itself, over its first derivative. So due to its simplicity and efficiency, it is most popular method in solving high degree equations. So let's also go and see the application or method in this example by using the Newton-Raphson method. So the first step is to put the given equation in the form of the function. Then its first derivative of the given equation. So we use, because here this is not this is equation, simple equation. It's not function. There's not f of x here. So first, before solution, we put it in a function form. We say that f of x equals 2x squared minus 5x plus 3. Then we calculate or find its first derivative. So the first derivative, f prime x, equals to 4x minus 5. Then the formula will be plugged in the code that will be in this form. So this is the function, and this is its first derivative, and this is the whole formula of Newton-Raphson method. Now let's go to our IDE and make this slight change and see the effect of this change on the solution. So let's actually will not change anything in the code except the definition of the function, as you see here. So we say x minus, the numerator is 2 multiplied by x squared minus 5 multiplied by x plus 3 over the derivative 4 multiplied by x minus 5. That's it. So now we have nothing will be changed. Just here we change the formula, and let's run the code and see the output. Actually, in order to compare, I don't want to erase or clear the window, command window. So wow. So here, see, root equals to 1 at iteration number 7. So if you remember, the value 1 was obtained at iteration number 62 with the simple iterations method. But here, with the Newton-Raphson method, we obtained the solution at only 7 iterations. So this is the meaning of efficiency, that you can get the solution at the very, very small number of iterations. Very good. Now, here we don't have another form. Newton-Raphson's method depends only on one form. So how can we get to the second root? So let's try to change the initial guess from 0 to 1.2, for example, and see the result. So 1.2 gave us the same solution at 7 iterations. Now let's try, for example, 1.4. 1.4 gave us the second root at 5 iterations. So here we can say that Newton-Raphson method does not need to make any change in the equation. All you have to do is to change the initial guess and make some guesses at the nearest points or most close points to the required solution. So simply, this is the code of the Newton-Raphson method. Maybe the simplest code, because you can make some enhancements if you like, but generally, like some messages or something, if there's not let's say conversion, or if the solution is not obtained. But generally, this is the simplest form, this is the simplest code of Newton-Raphson method. Now, in this method, we had to compute the first derivative. We had to find the first derivative. If we don't want to find the first derivative, if we want to make a function or script which takes the equation, the given function, and compute the roots according to the initial guess, without the need to compute the or let's say to find the first derivative. So in this case, we'd better to use another numerical method to find this derivative. So here we take a brief information about the finite differences approximation. The finite differences method, or finite differences approximations method, is a method used in order to find the derivatives of a function by taking the difference of f of x by the difference in x, which generally called step size, or h. This is the value of h, which is the difference between two adjacent x values. So actually, when we look to this point or to this figure, we see that geometrically this difference represents the slope of this line AB. So when we take the difference of f of x over the difference of x, this will be the slope of this line. And this slope will be equal to the slope of the tangent at the point A, for example, when the two values of x are so close to each other. That means if this point B approaches to A, for example, if B is located here, where I show the pointer here, so if B is here, the segment of line will be approximately equal to the slope of the line will be equal to the tangent at the point A. So in this case, the smaller the value of h, the more accuracy we can get by the finite differences method. Now, the finite differences, as I said, depends on the differences of f of x over delta x or h. So let's see here, as we saw in the geometrical form, the slope is f of x plus 1. This is point B, or f at point B, and this is f at point A. This is called forward finite differences. Why? Because actually, in order to find the first derivative at point A, at xi, which is point A, we took the next point, xi plus 1. So B was next to A in the positive direction of the x-axis. So we took forward, or looked forward, in order to obtain the point which we are, or the derivative at the point which we are. So again, for example, if I turn to the figure here, this is f of xi at the point A, so we want the slope, or want the derivative at point A, so we looked forward here at f of xi plus 1, and then the difference between f of xi and f of xi plus 1 over the difference between xi plus 1 and xi, which is called h. So this value will be the slope of the tangent at point A, or approximately the slope of the tangent at point A. And that's why it's called forward, because we took the next point, B, which is next to A, at the positive direction of the x-axis. On the contrary, there is another way to take, or to find the slope, is backward finite differences. This is by looking back. That means, suppose if you are at point B and you want the slope at point B, so instead looking forward in the positive direction of the x-axis, you look backward. You look to the point A at that point. So this is the meaning of backward. So instead of going further or directly in the positive direction of x-axis, we take a previous point, or a point at the negative direction of x-axis. So it will be f of xi minus f of xi minus 1 over h. Finally, there's central finite differences method, or equation, which puts the x of I in the center between 2 points. So it could be considered a combination of these two, or the previous methods. So here we make the difference between a point, 1 point forward and 1 point backward, and the delta x will equal to 2h. Why? Because actually we put xi in the center between 2 points, one forward and one backward. So actually, because the distance h is taken always between two adjacent values of x, so from x to xi plus 1, and from xi to xi minus 1, there's h at each direction. That means the difference will be divided by 2h. So this is the idea of finite differences approximation. Before applying it to the Newton-Raphson method, let's try to see the level of accuracy of each one of these three formulae. Now, find the first derivative. Sorry, take f of the equation of at x equals to 0.1. If the polynomial is f of x equal 0.1 x to the power 5 minus 0.2 x to the power 3 plus 0.1 x minus 0.2. So let's see the analytical solution first. So the analytical solution will be f prime x will be 0.5 x to the power 4 from this term. This term will give us 0.6 x squared plus 0.1. Now, when we substitute the value of x equals to 0.1 in the derivative, we'll get the f prime 0.1 will be 0.09405. Now, let's code this solution. In order to evaluate the values, it's easier to use this notation instead of using the subscript notation in the code, because that could be understood as using arrays, and it will be much complicated in this situation. We know that the point x of I is the current point x. xi plus 1 is a 1 h ahead, so it's x plus h. The point x, I plus sub I plus 2, actually is the current point x plus 2 h's or 2 steps ahead. This is the idea. Always look at it in the geometrical form. So x will be computed in terms of h. Simply imagine that, for example, x plus h here, that means we are adding h with multiplied by this quantity. For example, here, xi plus 2 will be represented by x plus 2h. In the same way, the negative direction, xi minus 1, could be represented as x minus h, or xi minus 2 will be represented as x minus 2h. So we're going 2 steps backward. So it will be minus. So this notation will be simpler to apply. Actually, we don't need to code a script for this equation because, as we'll see, it's easier to make a formula. So let's go to our command window, and try to see how to code this equations by using this notation. Let's return to the previous page in order to see the equations. So let's do something here. For example, let's call our function. First of all, we say df. Now let's do something here much easier. I forgot to copy the function or the given problem. So let's say f equals to at x 0.1 multiplied by x to the power 5 minus 0.2, sorry, multiplied by x to the power 3 plus 0.1 multiplied by x minus 2. So 0.1 multiplied by x to the power 5 minus 0.2 multiplied by x to the power 3. Okay, correct. Now this is the definition of the function. Now let's compute the first derivative. Now here we will compute the first derivative. We will have two important things in order to use in this solution. First, we should define x. So x is defined as 0.1. So say x equals 0.1. Good. We should define h. So let's suppose h is 0.1. Okay, small value. Generally, h is taken as small as possible in order to get higher accuracy, but sometimes very small values of h could lead to long solutions in some codes. So generally we try to find the best step size which give us accepted solution with good accuracy and in a good time of execution. Now let's say df forward, dff means the differential forward, equals to f of x plus h all and minus f of x all over h. So we notice here this is the solution by using forward finite differences. Now let's dfb, that means backward, and it will be f of x minus f of x minus h over h. So it gave us the value 0.98. So it's closer to the analytical solution. Now let's try the dfc equals to f of x plus h minus f of x minus h all divided by 2 multiplied by h. Now let's go to the analytical solution and see which value is closer. So it's obvious now, we see that the value obtained by means of the central difference is closer to the solution, because we see the forward became very it's not close enough. Okay, the backward finite difference is acceptable, but still there's big difference in the third decimal digit. But the closer value is the value obtained by the central difference. Now let's try another value of h. Let's say h equals to 0.05, and let's try the forward substitution, or sorry, forward finite differences. Now let's try the backward And finally, the center. Now, again, we notice that the central or the central finite difference yielded the best solution. For this reason, we will choose to use the central differences method with the Newton-Raphson method in order to solve the higher degree equations. Now, let's see how to use or how to combine the two methods together. So at first, we will recall the finite differences formula. Then here's the Newton-Raphson. So the combination will be by taking the left side of the central differences formula of the first derivative, and we will substitute it in the denominator here of the Newton-Raphson equation. So the result will be this formula. xi new will be xi, because we should unify the notation for all values of x or all x's, and then we'll see that f of x I plus 1 minus f of x I minus 1 will be the difference of x's over 2h. So this is the formula of the central differences. This formula will be transformed to the computer code form in this way. So we'll have x in u, as we saw at the previous slide, that xi will be represented by x because it's the current x minus 2h multiplied f of x. Same thing. And here also we represented or expressed the substitute or subscript, the subscript notation, but in terms of h. So xi plus 1, x plus 1, xi minus 1 will be x minus h here. Now let's make the modifications on the Newton-Raphson code. So we'll go to our editor. Here we will make 3 simple modifications, not more. 3 simple modifications. The first one is to put the function in its original given form, because the problem is it's 2x squared minus 5x plus 3. So our goal is to apply Newton-Raphson method without explicit manual derivation. Just given the function directly and it will do the rest. Then the second modification is to define h. So let's suppose that h equals to 0.05. Could be 0.01. This depends upon the accuracy level you need in solution. Now, the third modification will be writing the formula, the new formula of the combination of the combined method. It will be x minus 2 pi by h divided by f of x plus h minus f of x minus h. Now, let's execute the code. So we get the solution we expected. Actually, the same values at x equals to 0 as an initial guess, we obtain the root, the first root, at 7 iterations. Now let's make a change and assume that the initial guess is 2, for example. So the second guess gave us the second root at 6 iterations. So actually this is the combination of the two methods. Simplified the input because here we didn't have to make any differentiation directly. We gave the function, or they gave the equation as a function, and we obtained the roots by changing the input or the initial guess. The final stage of this tutorial is to change this code, this script, into a function, because functions are more flexible in usage and in call, because you can call it several times in one program. Also, it could be saved and as a part of library of, for example, numerical methods and so on. So we can use it frequently. So here, first, let's save the file. Here it's called Newton-Raphson. So here, I will save it as another name. I'll call it NR root Newton-Raphson root. So here we call the function NR root. So the changes which will be done, first of all, we will neglect all these things. And we will leave the loop. Also, we shall neglect the printing. And let's here add the head, or let's say the signature of the function. So function NR root. The name of the function should be the same as the file name which it is contained in. So, and also we should define the return value, the value that be returned to the user after he calls this function. And then we will define the function f, the x, the h, and the tolerance. That's it. Let's save this function and go to the command window and try to apply this function here. So let's say in our root, we will enter the function to the power 2 minus 5 multiplied by x plus 3. Now we pass the function as a parameter. That's it. This is the initial guess. The tolerance, the h, step size of finite differences is 0.05. 1, and this is the value. Let's try to run the code. Exactly, this is the solution. Now, if you want to see or return two values, because at the previous script or the program, we saw two results: the root and the number of iterations. So we can make here an array, a small MATLAB octave array. The first element will be x in u. The second element will be iteration. Now let's save this code. Remember, any modification made in the function should be followed directly by the save, because here we do not execute the function, we call it. So any change should be saved first in the file in order to be made or performed by the command window. So again, let's do some small modification here. Equals to, let's call it x and I, and x equals to 1 and I equals to 7, the number of iterations. Finally, let's add some default values, because sometimes we know that, for example, like tolerance could be as a default value. We don't have to enter the tolerance every time. Maybe also the step size. So actually, it's enough to define two things: the function and the first guess. This is the best thing. So let's save the function and go here. Instead of entering, our function will be very concise, because it will accept the function and the initial guess only. So the same thing. So we don't have to, but if we have another step size, okay, we can enter it, no problem. We can say 0.001, for example, and it will give us the same solution. So this is the function. We saw here how we can put it in the function. Also, we started from the very beginning of the simple iterations. We saw the Newton-Raphson method and the finite differences, and finally combined the two methods and saw how to code a script and a function of this combined method. Thank you for listening. I wish you have enjoyed this tutorial. Please subscribe. If you like this tutorial, don't forget to give me a like. Thank you for listening again. Bye-bye.